Okay, we're going to be completing the four-part lecture series for Chapter 28. This is for the ME260L course, which is Mechanical Engineering at the University of New Mexico, and I am Matt Plyle, one of the professors there. Okay, so let's talk a little bit about yield, fields, and chips. So what does it mean by yield? So if you think about it, we talk about crop yield and other kinds of yield. It's pretty much how successful you are, right? So if you have high crop yield, that means you get a lot of bushels of wheat per acre. In the case of semiconductors, we have the number of chips per wafer. Okay, so yield refers to the number of good electrical chips out of the total number that you can possibly make. Okay, and a field? Well, a field is what a stepper prints for each step it takes during the photolithography process. So when you use a stepper, you only expose part of the wafer at a time, and then you step those fields over the wafer. So in this graphic you see here, the blue squares represent the fields, and the little squares within the blue squares represent individual chips. Okay, so we call chips the actual circuits that are singulated or diced. They're cut up and packaged separately, so each of the little squares you see gets packaged in its own packaging, and then it's put into a circuit board or your cell phone or whatnot. Okay, so we use the term chips and die interchangeably. Okay, so at Texas Instruments we call them good electrical chips, and then at Philips Semiconductors they were good electrical die. So it just depends where you work as to what they're called. So yield calculation is very simple to do. It's the number of good parts divided by the total number of parts that should have been good or could have been good. Okay, and it's a simple percentage. Okay, now what I like about this graphic that I got from the University of Munich from one of their classes that they posted shows each layer of a process for making some sort of semiconductor device. So each layer has a photolithography step, has a deposition step, has an etch step, and you build up it layer by layer by layer by layer until you get through making the entire chip. Each layer can have defects. You might only have one or two defects on each layer, but if you have 50 layers, they can add up, okay, and cause a large yield crash. So if you look at the yield sub R in the bottom, you can see that it's a product of the yield of each individual layer. So you might say, hey, I'm doing pretty good because at the poly dep step, I only have 1% yield loss. So I have 99% yield. But if you do that at every layer, you go 99 times 99 times 99, right, percent, you end up with something like 80% when you're all said and done. So, that's 20% of the chips that should have been working end up not working. Okay, so it's always a job of a process engineer, the equipment engineer, and also the product engineer to work together to determine where the biggest yield hit is and then work on that, improving that yield. So when I was working at TI, we would usually start a new product and have about a 60% yield, which is barely breaking even for us. And then, we would fix things, improve processes and whatnot, and get it up to 96% yield, 97% yield. And then all of a sudden, the product engineers would say, let's shrink it. So if you make the chips smaller, you can put more chips on a wafer, get more chips that yield on a wafer, and life is good. But when you make something smaller, it's harder to make. So you may lose more chips or your yield may go down. But then think about it, 90% at 100 possible die per wafer is 90 good electrical chips, and 90% at 50 chips per wafer is 45 chips per wafer. So, or even if you're at 100% and you only can make 50 because they're bigger, you're still going to end up with fewer chips per wafer. So you're always balancing this this equation, right? If I make it smaller, I'm going to have a harder time making it. I'm going to lose more die, but then I get more die per wafer. So where's the sweet spot? Okay, and then you're always competing against other people who are also making smaller chips and making them better and yielding higher. And sometimes if you have innovative designs, you can get rid of one layer or two layers and still have a good working chip. And then if you have less process steps, then the probability of a defect is lower overall. Okay, so here are some links to websites where you can do these kind of calculations, these yield calculations. Let's go ahead and look at the Kali Technologies one first. Okay, I really like this website. I hope it's coming up on the screen. If not, I'll have to put it in later. So this is a die yield calculator. So you can put in your die width and then your scribe lines, how big your wafer is, how much you lose on the edge of the wafer, your defect density, right? Usually you have kind of a ballpark figure for your process and for your clean room. And then you can move the die around left and right and up and down to see how things work. We're not going to worry about that right now. So let's assume we've got a chip that is 15 millimeters by 12 millimeters. Okay. And then we say our horizontal scribe, that means the distance between adjacent die on the horizontal. Let's make it 0.1 millimeter, which is 100 microns, which is doable. Dicing blades typically can cut smaller than about 40 microns. So, and then you have some alignment issues and stuff and debris issues. So they typically want to make the scribes about 100 microns. At TI, we started at 100 microns, and then when I left TI, we were at 80 micron scribes. So we made the scribes a little bit narrower so we could fit a few more chips per wafer. Okay, so we'll make the scribes. We also call scribes streets because they kind of look like streets in between blocks. Okay, so now we put in those data and we can see we have a possibility of 26 die per wafer. Those are the green ones, including the black ones, right? And this is for a 4-inch wafer. Okay, so let's say, we're a fairly modern fab, so we have 8-inch wafers. 8-inch wafers are also referred to as 200 millimeter wafers. Okay, and then we say, well, from 5 millimeters in from the edge, we're not going to get anything to produce because we have clamping rings, clamping tabs, edge of the wafer effects, non-uniformities in the thickness, deposition of various materials and whatnot. So the edges of the wafers are really hard to control. So we call it an edge exclusion zone. That means we're not even going to try to make any chips in that edge. So when I was at TI, I think our edge exclusion zone was 3 millimeters. So let's go ahead and put that in. Okay, so you can see that the edge exclusion zone's a little bit smaller now, and we got a few more good die. And then defect density, right? We're saying, we got about, 0.1 particles per square centimeter. That's the density, number per square centimeter is 0.1. So for every 10 square centimeters, we can expect a big enough defect to cause a yield loss in that chip. Okay, if you can change this, you can say 0.2, which is pretty bad, right? Or you can say, oh, we're a really clean fab, so let's say 0.02. And now we only lose a few chips. Okay. And I'll let you guys play with the manual wafer placement in X and Y. You can kind of move things around to get it to fit. Now, when we were doing 6-inch wafers, we had a flat along the bottom of the wafer. So we would try to move these maps around to fit better. Okay? So anyway, you get the idea, right? And we can do a quick thought experiment. In this scenario, we have 68 maximum chips on the wafer. Let's say we do a 10% shrinkage. So 10 in X and 10% in Y. So we go from 15 to what? 13.5. And we go from 12 to, now we have 93. Let me see if that's right. We went from 15 and 12. Yeah, we had 68, and then we just did a 10% shrink on the die size in X and Y. So that was 13.5. And 10.8. Oh, 84. So 67 or 68 to 84. So we gained a bunch of chips, right? And that's all profit. So, you know, it's roughly 20% increase or more, 30% increase in the number of die per wafer from what we used to have. And if we don't change our price, that means it all goes into yield. All right, let me go back to the PowerPoint. Okay, and then this other one brings you to a website that talks about the calculation. So the math is in here, so you can use that for your homework as well. And you can also model it with their model and see what you get. Okay, so you can use those two different calculators to get a feel for, you know, how the design affects the yield and the possible number of wafers per chip and ultimately profit. All right, so we talked about yield, die, and chips and how many you can fit on a wafer and a little bit of an idea of what the edge exclusion does to yield and what the defect density does to yield. Now we're going to talk a little bit about processing. So we went into detail on photolithography in an earlier lecture, and there's several other photolithography lectures you can find on YouTube, and then also my grant, the Southwest Center for Microsystems Education, also known as the Support Center for Microsystems Education. We have some lectures also on our YouTube channel. All right, so if you want links to that, let me know, and I can direct you to that. All right, let's talk about etching. So there's different kinds of etching you can do. And remember, etching is the removal of material. So with photolithography, you pattern the wafer, and as you pattern the wafer, you create zones that are protected and areas that are not protected by the photoresist, right? Photoresist stands for photons, so it's sensitive to light. And resist means it's resistant to etching. Okay, that's why we call it photoresist. So the etching process is usually after the photoresist patterning step. And whatever is exposed, right, that's not covered by the photoresist is what gets etched away. And the stuff that's covered remains on the wafer. So we have different ways of removing material depending on what type of material it is. Okay, and what is the most cost effective. Okay, sometimes we do more expensive etching if we have to be more precise, and those are called critical layers. And then other process steps, they're non-critical, so we don't care about the size as much. So we might use a bulk etching method like a chemical etch. Less controllable, but we really don't need to control it that well. So sputter etch is a physical removal of material by accelerating ions to the material towards the wafer, and it'll remove both photoresist and the material in question, but you have to have enough photoresist available to protect what's underneath throughout the etch process. So the open areas get etched faster. Then we have chemical etches, so the photoresist protects where you don't want the chemicals to interact with the surface, with the material you're trying to get rid of. And then the open areas in the photoresist are available to get etched away by the chemicals. And then we have ion etching of different types, reactive ion etching, and ion etching with an inhibitor, such as the deep reactive ion etching process, also known as the Bosch process, named after the company that invented it. So here's a cartoon of how sputter etching works. You have an ion, you accelerate it in some way, and that's usually through an electric field. So you make let's say an argon atom, an ion, by stripping off an electron, so it's positively charged, and then you can put a large electric field inside the chamber, and it accelerates the ion towards the wafer surface. So the wafer might be at ground, might be grounded, and then where the ions originate might be at a positive charge, so that they repel the ions and the electric field lines go from the cathode all the way down to the anode, where it impinges on the wafer. Okay, so you accelerate the ion, it hits the material and knocks off a piece of that material. It'll also hit whatever you have protecting it. In the blue that you see here, okay, is your hard mask, and it can also be a photoresist. So it just depends on the chemistry and what you're trying to etch. Okay, you can also do a chemical etch where you put the wafer in a bath, and the chemicals themselves will react with the material that's available to it. It will create a new molecule, right? It'll react and combine, and then that comes off of the surface. And those tend to be isotropic etching, which means the same etch in all directions. So you get this hemispherical or this dish-like etching there. You can have wet etching, chemical etching that is anisotropic, that has definite directionality. Then you have ion enhanced. So this would be a combination of a chemical and an ion to produce a volatile product. You can do very directional etching with this by setting up the electric fields properly, so you can get an etch that's almost perfectly straight going down. And then ion enhanced inhibitor. What that means is you etch a little bit, and then you switch the chemistries over to create a layer to protect the sidewalls, and that's what they label as the inhibitor. Okay, so you etch a little bit, then you coat, you etch, you coat, and you switch back and forth between two different gas systems in your chamber, and you can slowly etch all the way down into the silicon. Sometimes they even etch all the way through the wafer with these sorts of processes. And again, this is the Bosch process, is based on the Bosch process. Reactive ion etching combines ions with reactive components, so you generate an etchant species that gets to the surface of the wafer through adsorption. That means it sticks to the surface. It doesn't absorb with a B, absorption. Absorption would mean it goes into the wafer itself. Adsorption means that the material that's doing the reacting is sitting on the surface. So it collects on the surface, it bounces around a little bit. There's a lot of surface dynamics and chemistry going on. Usually you're doing this under some sort of temperature, and eventually the conditions are just right for a reaction to occur. So those etchant species react with the film that you're trying to etch away, creates another compound that's desorbed off the surface, and it goes into the gases in the chamber and gets pumped out. Okay, so that's reactive ion etching. This is a cartoon or a schematic of the deep reactive ion etching. Again, this is the Bosch process. So we're switching between etching and an inhibitor, and we're going back and forth, and you can see the scalloping that happens. So you can see these little bumps here. So you can actually count the number of times it's switched from an inhibitor to an etchant to an inhibitor to an etchant as it etches down into the wafer substrate. Now, this was critical. This invention of the Bosch process was critical for the dramatic cost reduction in DRAM chips. Some of you may be old enough to remember when memory was very, very expensive, and the gamers and people who use their computers a lot would want to increase the random access memory, and so they would buy additional DRAM chips, and you could pay hundreds of dollars for 16, megabytes of DRAM. Nowadays, it's extraordinarily inexpensive, and part of the reason for that is the Bosch process. So we used to make memory units on the chip. Basically, we would store an electric charge on a capacitor, and if the capacitor is horizontal, right, it takes up a certain amount of space on your wafer. Now, if I can take that capacitor and make it vertical into the wafer, I can pack more capacitors next to each other, or more memory units. So we can make the density much, much higher for the same surface area on the wafer. So now we're making smaller chips with more memory capacity on the same wafer, so we can sell them for less money. Okay? So the Bosch process allowed you to make vertically oriented capacitors to hold charge, to hold memory bits. Okay, so here you can see a test structure where they've etched highly vertical lines into the wafer. This is quite extraordinary when you think about it. These are only 10 microns or so wide, and you can go to the right side of this cartoon here and you can see very, very thin and very vertical structures, and on the left they get wider as you go from right to left. Okay, here's another example of a cryo dry etching. So this is a rotor and a stator. So this is one of the first electrical motors made on a very, very small scale. So here we're talking a couple of 100 microns maybe across, or 100 microns across, something like that, which is the diameter of the human hair. Okay, so they have to keep the substrate very cold in this process, so they typically use helium or liquid nitrogen to do that. So another thing you got to do when you're processing is connecting the metal lines from one layer to another, especially with computer chips. Right? You make your transistor, which consists of the N and P junctions with a gate, right? So you can turn the gate on and off to turn the transistor on and off and go from a 0 to a 1 state and whatnot. But now you need to connect all these transistors, and you need layers and layers of metal lines, right? Think of wiring up a circuit board, something like that. You have lots of little lines or little wires going from thing to thing, and you can do that on a micron scale as well. So one of the steps you have to do is make a hole in your insulator. So you have one layer of metal, you pattern it, you have a nice wiring diagram, right? And then you add some insulator to it, usually an oxide of some sort. Okay, an oxide is like a glass, so it doesn't conduct electricity. And then you put another layer of metal down. But now you have the problem of, how do I connect the two different circuits together? Well, you got to put a hole in that oxide in between. So you put your first metal layer down, you pattern it, you etch it, you get your circuit from the first metal layer. Then you put your oxide in between that and the subsequent other metal layer. But before you put the other metal layer on, the metal 2 layer, you have to put holes in your oxide. So that's what we're talking about here. So the holes you make in the oxide are called vias. So vias are the holes that connect one layer, one electrical layer to another electrical layer. And one of the homework questions asks you to define vias, or what vias are. Okay, so that's what it is. Okay, so how do you do that? Well, you can use wet etching to make a via, or you can do a combination of wet and dry etching. This shows you an isotropic wet etching, okay, to start making that hole. So typically what we do, and what we did at TI, was we did a wet etch followed by a straight anisotropic etch. So we get something that kind of looks like a champagne glass, right? So it comes up very thin, and then the top of it is bowled out, and that makes it easier to flow metal into the hole. Remember, we're talking about very small structures. So if you can't flow the metal or you can't deposit the metal into the hole properly, then you won't make that connection from the one layer to the layer below. Okay, so there's a lot of details in that devil of making holes. You can also do anisotropic etching. Here we're etching the crystalline silicon with potassium hydroxide. So potassium hydroxide etches the 100 plane much faster than the 111 plane. So you can create structures that look like upside down pyramids. Okay, and if you make a bigger mask hole, you can have it go deeper, and you can even make some nozzles that way. Or you can make slots, right? Again, you're leveraging the crystallography, but you're using wet etching, which is very cheap to do. And then, of course, here you can make a nice straight hole, anisotropic with deep reactive ion etching, and you can go all the way through the wafer that way. If you set up your process properly, you'll make very straight holes. So they have really high aspect ratios. Aspect ratio is the ratio of how tall something is to how wide it is. So, you know, when they were selling etchers back in the day, they would advertise 100-to-1 aspect ratios, which means, you know, you can dig 100 microns down with a 1 micron wide structure, which is really neat. So here's some real images. Okay, so they're scanning electron microscope images. That's what SEM stands for. And it shows some highly selective deep reactive ion etching examples. So this is a National Science Foundation logo that we have on a metrology mask that we use in the clean room. So what we did was we patterned a very thin layer of silicon dioxide with photoresist, and then we etched the silicon dioxide away, which made it a masking material. And then we subsequently etched it in a deep reactive ion etcher. So you can't see the silicon dioxide on top. That's protecting the silicon underneath. Okay, some other pictures you'll be able to see it. So it's a very thin layer that's protecting this really radical etch underneath. And it's highly directional, so you can see, you can make very tall, thin structures. So as a mechanical engineer, you can think about making very small springs that way, coiled springs perhaps, right? Anything that's straight, that needs to be straight and thin, you can do that with deep reactive ion etching. So here's a close-up of it. Okay, you can see we've got about a 16 micron width, okay, at the top, and 16.7 micron at the bottom, which is really good. And the depth here is roughly 80 microns or so. So we've got a really good aspect ratio. Now, the way we got this picture was we had to cut the wafer across the structure that we etched and then put it on the side so we can look at it in a scanning electron microscope. So you can see even our cutting blade does a really good job of making a nice smooth cut. We get a little bit of chipping here, okay, but we're using a mechanical diamond saw. So think about that, right? Very nice smooth cuts. If you look at it with the eye, it looks like it's a mirror finish. Okay, here's another example. This is part of that same pattern. And what I like about this, you know, we put some letters in the pattern, and the top of the pattern, you know, part of it is an eye with a dot. And you can see that we can make a very long, thin structure, and it's still standing, right? It's not falling over or anything. So if we zoom in on it, you can see the scalloping of the deep reactive ion etching, where we switch from an inhibitor to an etch to an inhibitor to an etch. And we can go all the way down to the bottom. Okay, and you can see at the top this very well-defined square. Okay, and it has a thin line here. That's the silicon dioxide. That's protecting the stuff underneath. So here's a close-up of it. Very thin layer. We're talking you know, maybe 2,000 or 3,000 angstroms, something like that, on that order. So that's enough to keep the deep reactive ion etching from interacting with the silicon. And then you get some weird effects when you first start etching, and then you come down and it becomes pretty consistent. So this shows you that 10 cycles get between the inhibitor and the etchant gases gives you about 5 microns depth. So you can kind of get an idea how deep you go for each cycle. And then as a process engineer, you can change the timing of it. If the etching is too much retrograde, or if it starts to flare out, you might want to adjust the gas flows, the pressure, the temperature, the power, and the time for each of those steps. Then here again is another view. You can see we have some sort of defects down here. This is what we call grass. And then in the thin structures here, we have a lot of grass. So you might ask, well, where does the grass come from? This is what it looks like. What happened here is we didn't clear all the oxide. So we had little tiny specks of oxide that we didn't etch away where we wanted it etched away. And those little specks remained on the wafer surface and protected the silicon underneath. Okay, so here we cleared, so we could etch all the way through. Here we left some oxide behind, and we get this weird grass effect. Okay, and that was really a combination of the photolithography with the subsequent silicon dioxide etching. And there's a close-up of it and a further close-up. Okay, so that's, you know, in a nutshell, that's most of etching. Right? And then if you become an etch engineer or process engineer, you will learn tons and tons more about the equipment, about the gases and the pressures and all of that. So we can also change the electrical properties of silicon by implanting them. We implant them with boron, for example. We can make it N-type. I think it's boron is N-type and phosphorus is P-type, but I'm not sure. I always get those confused. But anyway, by implanting the silicon wafer, you can change the electrical properties, because now you're adding either a donor, right, an extra electron. So if you put one type of element in there, it's got an extra valence electron, so that's free to move around. So now all of a sudden that crystal is no longer a semiconductor, but it's actually a conductor. And if you go the other way, where you put in an element that has 3 valence electrons, then you have an extra hole that, you know, things can fall into. Well, how do we do this? How do we make a machine that can implant ions into a crystalline silicon? So we need an ion source. So that's shown in the cartoon there. And then we need, once we create the ions, we got to move them. So you move ions with what? An electric field. Okay, so once I have an ion, it has an electric charge. You put an electric charge into an electric field and it'll start to move. Okay, and if you can get it up to 10,000 volts or so, you can really get those ions to move. So they gain an energy, in this case, of 10 kiloelectron volts, for example. So they're humming along, right? So each ion has an energy of 10 kiloelectron volt equivalent, which is the energy that's gained by moving that particle through a potential difference of 10,000 volts. And the speed of that ion depends on the mass as well, right? So kinetic energy is 1/2 mv squared. So you can do the math. You can calculate the speed of the ions, right? You know the mass of the ion, and then it's trucking along. Now you usually put it through a magnetic field, and what happens when you have a moving charge in a magnetic field, it feels a force. So depending on the speed and the amount of charge that the ion has and the mass, you can bend it at various amounts depending on the magnetic field. And the idea there is you let the ions fly through this magnetic field, and you're going to have some ions that have 2 electrons removed from it that maybe aren't of the species you're interested in. There might be some other contaminants that you've ionized as well and whatnot. So by putting these through a magnetic field and flying through a magnetic field, they'll spread out depending on the mass and the velocity and the charge, and you can select the specific type of ion you want. So that's what it's showing there. So that specific ion will come through the aperture when everything's tuned up. So now you've only got one type of ion with one type of energy. So you control the depth that the ion goes into the crystal, right? And so that you can actually drive it into a certain depth by changing its velocity. Okay, and then you also have a nice beam at that point. So after the aperture, you have a nice tight beam. Then that beam goes to an XY deflector. Again, you can change the course of that ion beam by changing the electric field, and you can actually paint the wafer in X and Y with an ion beam. So that's what this is showing. So you can actually dope your wafer to a specific depth and a specific doping level. Okay, so the more dopant you put in, the less resistive the material is and the more conductive it becomes. Okay, so you can make diodes this way by selectively implanting certain areas, making some areas P, some other areas N. You do this with masking. You do a hard mask, say a silicon dioxide, hard mask. So the dopant goes into the silicon dioxide, and it also goes into the crystalline silicon where it's open, right? Remember, the mask is open in some areas. So the parts that are covered, the ions go into the oxide, which is later stripped away. All right, so here's the next part of part 4 from Chapter 28 lecture. This is how to make a PN junction diode. So again, we're doing layer by layer. We're doing process steps, and if you start at the top, right, where it says number 1, and work your way down to where it says number 9, you can get an idea of how a PN junction is made. And diodes are used for all kinds of applications in electronics. So we start with bare silicon wafer, so crystalline silicon, pure crystalline silicon, and we dope it to be N-type. Okay, and that's how we buy our wafers at the semiconductor fabrication site. They already come doped, and then we go ahead and we grow some oxide on it. Okay, so what do you mean by grow oxide? Well, we subject the bare silicon, the crystalline silicon, to heat and oxygen, and you can grow oxide. So typically silicon will oxidize just like rust forms in iron, right? Iron oxide, FeO2, we create SiO2. Now, if you just leave silicon out in the air, it'll grow a thin layer of native oxide, which is usually a couple of nanometers thick, and then it stops growing. You may ask, well, why does it stop growing? Well, you need the oxygen to get into contact with the silicon. So as the silicon dioxide is growing on top of the wafer, it's also masking the oxygen from getting to the substrate or the silicon to form more silicon dioxide. So it actually grows from the surface down and up a little bit. So it kind of grows like this. I hope you can see that in the little video clip. So, when it gets to a certain thickness, it just stops growing. Now, we can increase the thickness of the oxide if we put it in temperature. So if you ramp up the temperature from room temperature, which is about 20 degrees Celsius, and you ramp it up to 1,000 degrees Celsius and put it in an oxygen environment, then the oxygen is now moving at a much faster rate, right? Because higher temperature means the molecules and in the air are moving much, much faster. So now those oxygen molecules have a lot more energy, a lot more speed, so they can diffuse through the oxide layer you've already created much more easily. So as a result, you can drive some of that oxygen to the silicon oxide interface and cause more silicon oxide to grow. Okay, so raising the temperature helps a lot. You can also use water vapor, right? H2O molecules are much smaller than O2 molecules, so you can deliver the oxygen using water molecules. Water molecules are also less massive, so water molecules at the same temperature as oxygen molecules are at much higher speeds, right? Because temperature is proportional to the kinetic energy of the average molecule in an ideal gas. And as a result, the lighter molecules are moving faster. And the lighter molecules tend to be smaller. So smaller molecules can go through oxide much easier than big molecules. And they're also moving much faster, so they have a better probability of getting through the oxide layer and actually forming on the surface. So you've got some homework that talks about oxidation growth, and they have some oxidation curves for wet and dry oxidation. And that's the difference. The wet oxidation is with water vapor. The dry oxidation is with just O2, regular oxygen gas. So once you grow the thickness of silicon dioxide that you want, you apply some photoresist to it and you pattern it, right? So that's steps 3 and 4. So where the light goes is where you're going to have a hole in your photoresist. So in step 5, after develop, you can see the hole in the photoresist on top of the oxide. Okay, so now that hole is exposing the oxide underneath. Then we can go ahead and do a silicon dioxide etch. And we use typically a wet process called buffered oxide etch. Buffered oxide etch is buffered hydrofluoric acid solution. Okay, and that's really good for etching silicon dioxide. Okay, but it'll only etch where it's open, where it's exposed to the chemicals. So after step 6, when you do the etch of the silicon dioxide, you no longer need the photoresist. So you remove the photoresist in between 6 and 7. Okay, and now you're left with the silicon dioxide pattern that has a hole in it. So now I'm exposing the silicon underneath the silicon dioxide where that hole is. So then I do a boron implant. Okay, and boron creates a p-type semiconductor. So the boron ions are accelerated like we talked about before, and they go very quickly and they're driven into the silicon crystal. Okay, and they're also driven into the silicon dioxide. But once you remove the silicon dioxide, you get rid of the implanted silicon dioxide, and you're only left with the implanted silicon underneath in the regions that you've defined. And that's how you make a PN junction. Okay, so it's fairly straightforward, but of course the devil is in the details. Each one of these steps, usually has a few process engineers in charge of it, along with 1 or 2 equipment engineers that monitor the equipment that's used for that step. And so you can see that, in a typical semiconductor factory, even a small one, you may have 100 process engineers and 20 to 50 equipment engineers, making sure everything runs smoothly. And so you can imagine that you have to work very well together on teams. When there's a problem, you've got to identify where the problem is and what area can fix it, or maybe it's a combination of process changes to make that process better and drive the yield higher, right? We always want high yield. Okay, so here's a within chip level 0. So this is how you can make connections inside the chip, and that goes back to our discussion about vias. So vias make the connections between the different electrical lines. You can see it in this little gray graphic here, the first one on the left, the first little picture. you can see 2 layers of metal, and you see the little tiny divots in there. They look like little holes. Those are actually the vias. So the metal is filling in the vias, and it makes it look like the metal has a dimple in it or a dent, right? And that's where the via is. And so you can see the connection from the light gray to the darker gray layer. And if you look closely, you can even see another layer of metal underneath that. So there are 3 metal layers that I can discern in this image. Okay? And that's how you do the interconnects. The other cool thing about this photograph is that there's a lot of topology there. So as you create layers and structures, and then you put dielectrics in between or oxides in between as an insulator, right? Because you need to insulate one wire from the other wire, except where you want to connect through the vias. You can get a lot of topography, so you start to get these bumpy regions. So you can actually see the topography showing up in the bumps in the metal. Okay, so usually after a few layers of metal, you need to planarize, so the next layer of metal is flat. If it gets too bumpy, then it's harder to process, harder to focus. The depth of focus becomes an issue and whatnot. Okay, so that's the level 0 within chip, right? So level 1 is where you connect chips to each other, and then you package them. Then you put them in printed circuit boards. That's level 3. Level 4 is you take the printed circuit board and you put it into the chassis or box. If some of you have ever opened up an old PC, you would have slots with different circuit boards in it. That's the level 4. And then the level 5 is the entire system together, right? And that would be your computer system. So that's the hierarchy. So here are some metal interconnects. So we're etching some holes. Okay, and we've got completed transistors. So we're going to make some holes to those transistors, to the PN junction, as well as to the gate, right? So we got a PN and a gate, right? Or we got a channel and 2 N areas in the substrate. Now we're going to add the metal. Okay, this is showing you the metal as posts. It's not quite like that, but you get the idea. And then actually those posts were the metal in the holes themselves. And then we add the interconnects. So now we're connecting different transistors to each other to make our AND gates, our NAND gates, and all of that. Okay. And in reality, this is what it looks like. So they've taken a chip, right? And they laid it on its side and they cut it across, and you can see all the different metal layers. So if we count, right, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, about 9 metal layers. This is a very complex logic device. Okay, and each layer is between 1/4 and 1 micron thick. Okay, typically the layers are very, very thin. Okay, and so, you know, it's like 2.5 dimensions. It's mostly in X and Y and a little bit in Z. Okay, so you can get an idea. And what's really cool to note here, it's the alignment. So if you look at the 9th metal layer and it's aligned to the 8th metal layer, you can see how well aligned it is. It's unfortunate it doesn't have a scale in the X direction, but I would venture to guess it's probably around 1 micron at this left uppermost lead. That's metal lead that's cross-sectioned. So this is probably around 1/2 micron, the via. So the 1/2 micron via hole has got to be aligned, you know, to the level 8, okay, which is slightly smaller than the level 9 lead. So alignment's real important. You can tell it's not 100% perfectly aligned. It's shifted a little bit to the left, but not much. So they have very good alignment tolerance there. And you can imagine if your alignment is off, you're going to miss or only partially make the connection, and then you won't get good connectivity between the different layers. So alignment's real important as well as the critical dimensions. Okay, so you can see how complex it is. Here's another image I found on the internet. It's a little bit more 3D-like, but you can get the idea of how the different metals are aligned. Okay, so they have metal 7 and metal 6, and then they show the via from metal 6 to metal 7. And again, vias are the holes in the oxide, the holes in the dielectric that are between the different metal layers. Okay? And this is a 0.1 micron technology. So this is fairly modern technology here. When I was in the business, the smallest thing we made was a 0.5 micron. Okay, but of course, as you get smaller, it gets much, much more difficult. And I really love this image. This is a colorized scanning electron microscope image. So you can see the metal. It is grainy. So we talked about metal grains in some of the subsequent or previous chapters that we looked at. And the grains, you know, and the grain boundaries dictate the mechanical properties of metals, but it also dictates how well the metal acts as a conductor. So in semiconductors, we were always looking at grain size as an important metric to monitor and control. The way we measure grain size was by reflectivity. So you can imagine as the graininess of the metal changes, the reflectivity of the material changes, and the amount of light that gets scattered changes as a function of grain size and how grainy something is. So bigger grain size, a different reflectivity than smaller grain size. So the problem we had is if the grain size wasn't consistent, then the electrical properties weren't consistent. So you can imagine you could create metal layers that are highly resistive, which isn't good because now when we're driving current through it, through a highly resistive conductor, that means it's gonna heat up more, and you're gonna get power loss, and you're gonna have to use more of your battery. So there's always a driving factor to get better conductors, make them thinner, right? But thinner conductors also have higher resistance, so it's always a balance. We can't use gold because gold actually is a metal that can move in the crystal and silicon. So gold contamination of the crystal is really bad. It's a reliability issue. Copper is the same way. Aluminum, not so much. So we used to use aluminum a lot as a conductor. Then they came up with a Damascene process, which allows you to use copper, but they use a barrier metal. So they put a thin layer of a metal. I think it's titanium tungsten. We called it tungsten. It's abbreviated TIW, right? So titanium tungsten we put down first, and then we put the metal down, the copper. Copper has low resistance, but high mobility. But the titanium tungsten keeps the copper from migrating and creating what are called hillocks over time. So that's why titanium tungsten is called a barrier metal. Okay, so you can see there's a lot of interesting things you have to know to be a process engineer in the etch group and in the deposition group working with metals. All right, so we have wafer level electrical tests that we do, and this shows, this is actually labeled a little incorrectly. This is taken out of the book. What they've done here, they've already done the electrical tests on all the chips on the wafer, and then they follow it up with a ink probe, and they're inking the die that are bad. So you can see a few dots on here, ink dots showing where they're a bad die. And that was the old school way of doing it. You would just mark the bad ones so that the machine vision systems later on wouldn't package the bad die, the ones with the black dots on it. Now, of course, they don't use ink anymore, and they actually track the wafer maps, and they know exactly which chips have passed and which haven't passed. So now when they dice the wafers up, they cut them up, they know which ones to package and which ones not to. An important note is if I were to package all the wafers, or I mean all of the electrical chips, the good and the bad ones, and then test them, it would cost twice as much to throw out a chip. So packaging typically costs almost as much as making the chip itself. And so the packaging part of the process, there's a lot of money and effort put into that. So you want to only package the chips that are good, right? So that's why we do wafer level testing. Okay? And then, of course, once it's packaged, we test it again because we don't want to put a bad chip in a circuit board, right? All right. So how do you connect the chip, to the outside world? Well, you got to do something called wire bonding. So this is a great scanning electron microscope picture of wire bonding results. So you can see on the right side where the wire connects to the computer chip, and on the left side where it connects to metal pins. And those are the pins that are bent and come down so you can put them in a circuit board. So some of you may be familiar with chips and circuit boards if you had any kind of an electronics class in high school, or maybe you did some electronics classes at UNM. That is what's inside the package, right? So you got to connect from those metal pins that go in your circuit board to the computer chip itself. And you can see two different bonding techniques. On the left is wedge bonding, which it's just pushed into the pin, and on the right is ball bonding. Probably ultrasonic, when you put a little pressure and some energy into it, and it fuses with the bond pads. So these are little pads that you connect to that are around the side of the chip. Okay? And here's a close-up of it. So you can see the bond pads on the lower part of this scanning electron microscope picture. These bond pads are connected to the computer circuit, the chip circuit itself. And then this wire is connected to a pin in your packaging system. So you can notice we got two wires going to the same pin. You might think, well, that's kind of crazy, right? They're going to short out. Or why bother with that when you can just connect it onto the chip itself? Well, that's probably a ground, right? So you're going to have a common ground, perhaps. So several parts of your computer chip will be grounded, and other parts will have voltages going in, and other parts will have signals coming out. Okay, here's a close-up of the wire bonding on the bond pad itself. Remember, these big structures here are called bond pads. This is approximately, if I had to guess, 100 microns by maybe 75 or 80 microns in length. So it's pretty small, right? Remember, human hair is probably close to 100 microns. So this ball bond here at the base is a little bit smaller than a human hair cross-section. Now you can see there's this open area, and then there seems to be a frame around it. Well, all of this chip is covered in glass at the last step, and then we open up where we're going to make the connection. So the chip itself is sealed from the environment with a glass coating, which is patterned and opened only where you're going to make your electrical connections. Okay, and this is from Micron Technology, which is in Utah. Micron used to make the best PCs on the planet, and then they started making DRAM chips and made tons of money on DRAM chips. TI could not compete with Micron. We tried, but they always seemed to be able to make cheaper chips and more of them and higher yielding. So that's how they got all their money, and now they're making flash. So they've been in the memory business for a long time, and they've actually partnered with Intel to make with a company they call IM Flash. So they make memory chips. So just about every phone and every widget that you have that has memory in it uses IM Flash technology. And that's in Utah, right? And I think IM Flash is now expanded into the Rio Rancho site, so they're making some of those flash chips up in Rio Rancho. All right, here's a cartoon of the wire bonding process. So here we see the bonding tip with a gold wire that goes into it. It has a little ball bond at the end of it. Okay, there's a clamp here. There's an arc generator. You bring the ball in proximity to the bond pad and you create a very small arc, and it forms the gold ball, and then that's pushed onto the bond pad. So you get those connections. So we apply some heat. We can also apply ultrasonic vibration to basically melt the wire and push it onto the bond pad so it sticks. Okay? And then we go ahead and we move the head over to the package lead, and we just push down on that with some force, and then we break the wire off and we've got a connection. And if you watch these bonding systems work, they're highly automated and they look like a sewing machine. And they're very, very quick, and they can make some complex connections that are just remarkable. This is the classic dual inline package. Okay, and you can see the cartoon here shows those connections we saw in the scanning electron microscope picture before. Okay, so the bond wires are connecting from the chip to the lead frame itself. Okay. There's also ceramic packages. So ceramic packages are a little heavier duty. They may go into high temperature applications like car engines and that sort of thing. So, you know, the ceramic isolates the chip better, and it also allows the heat to either be transferred away from the chip itself and protect the chip also from chemical interactions due to its ceramic nature. Okay, surface mounts, so you can either use the dual inline package kind of thing where the little pins go into the circuit board and then you put a little bit of solder on there. But you can also do butt joints and gull wing kind of connections and crow's feet. It just depends, you know, how small the chips are, how closely you have to pack them together. You'd use different types of packaging and surface mount techniques for a cell phone, for example, than compared to like a computer that has more space, you know, availability. So the cost, of course, always goes up whenever you make things smaller and tighter tolerancing. And then here's your ball array bonding. So you put you have your connections all on the back of the chip here, the bottom of the package, and you have all these solder bumps, and then you push it down onto the circuit board to make the connection. So this is called a flip chip. Right, so we flip the chip over and then we push the connections down onto the package. Okay, and then once it's connected, then we put some epoxy around it to seal it off. It keeps the environment away from those metal structures and keeps the package nice and hermetically sealed. And having it hermetically sealed is real important because you don't want your chip to fail in 5 years if it's out in the environment, right? And it's exposed to humidity and temperature variations and whatnot. If you seal it up really good, those chips can last for 100 years, right? I had a microwave oven that was solid state, and it lasted more. After 30 years, I got rid of it because it was big and ugly, but it was still working. So all of those semiconductor chips were still working fine, just like the day I bought it. And cars too, right? A lot of the electronics in the cars will last 20, 30, 40 years. All right, so here's some more cartoons of different types of packaging. So if you're interested in packaging, and you know, that's a great field to go into. There's not a lot of university level research in packaging. It's, you know, some professors think it's boring, but that's where the money is, right? If you can come up with a better package and save 50% on a package for a computer chip, that's huge, right? That's about 25% of the total cost of the chip that you saved. So if you have a $5 chip, you can sell it for $350, you'll take all the market share, right? Because people buy millions of these things to put in their cell phones and whatnot. Okay, so here shows some more kinds of packaging. You know, there's a lot of variations. Okay, so this shows you a real printed circuit board with a bunch of different chips in it. Okay, and they have different kinds of connections. Okay, so even on the same circuit board, you'll have different sorts of packaging and connections depending on what you're trying to do. This is a relatively old circuit board. It shows an Intel Pentium chip. I think a Pentium was probably 30 years ago, something like that. Okay, so now if you look at the main CPU boards, they look a lot different. Okay, here's an Arduino. Some of you may have played with Arduinos. They're nice little packages that allow you to connect things from the outside world and also connect to other logic devices. So Arduinos are used a lot in robots. They're used in translating signals from analog to digital and then output to, say, LabVIEW or something like that. I've got a buddy at Ivy Tech. His name's Andy Bell. He teaches engineering technology. And that's what his students learn, is how to interface Arduinos to the real world through sensors and then interface it to LabVIEW so you can actually acquire and analyze data with it. And, you know, you might say, well, I'm a mechanical engineer, I don't care. Well, if you're working with robots, if you're trying to, you know, take information in and out of your mechanical systems, it's good to know a little bit of this stuff. And now there's even a flexible Arduino system. So this is kind of nice for wearable electronics or maybe bio MEMS applications where you might want to put a circuit system for a patient and then stick it to them so you can monitor their health. And then maybe after a week the sticky circuit falls off when you don't need it anymore. So for post-operative monitoring, it's really good. They're playing with systems so they can send patients home earlier and be able to monitor them on the fly. And not have to have them hooked up to things in the hospital. So if something gets a little wonky, if the temperature moves or the blood saturation level changes or the insulin level, changes or whatever you're trying to track, these kind of flexible electronics, would be able to phone home, call the doctor, send the data over. Know if you're having a problem, if your heart rate changes, whatever, and then call 911 if need be. And we can automate all of that stuff. So that'll help keep the costs down. Your recovery rate will be better if you're at home, usually, than if you spend more time in the hospital because you can get other kinds of infectious diseases and whatnot from staying in the hospital too long. All right, so that's about it for this chapter. I hope you learned something. I know I went through it kind of quick, so it's always good to augment the lectures with some of the reading, right? Try to read the chapter. It'll start to make more sense, hopefully, now that you've heard the lecture. And then, any topic that's interesting to you, just go ahead and Google it online, and you can find tons of YouTube videos, articles, companies that make these different devices, and learn from that. I found company websites to be very interesting. I like to look at them, not just for what technologies they have and what they're good at and known for, but I also like to look at the job listings to see what kind of skills and knowledge an engineer needs to have to be able to get a job at these places. I also look at it from the perspective of technicians. So there's a trend in industry to hire engineers as technicians, since we're not producing enough technicians coming out of the 2-year electronics type schools. So there's a gap there. So if you know, if you're not wanting to be a really high level engineer, let's say you're an average student, you like hands-on stuff, don't throw out the idea of being a tech, because techs can get paid a lot. I've known technicians when I was in the industry about 20 years ago, 20, 30 years ago. I worked with technicians that made more than me at the time. They were senior techs, very, very good at fixing equipment and understanding processes, and they were getting somewhere around $80,000 back then. And I've heard from my buddies at Global Foundries that a lot of the senior techs now are making $150,000 to $200,000 a year. And that kind of makes sense. If you're taking care of a $100 million piece of equipment, right? Think about it. If you're really good and you can keep that machine up and running, even 2% more, you're going to pay 10 times your salary back to the company. So they know that those high level, very experienced technicians are worth their weight in gold, or actually in platinum now. So, you know, being a tech isn't a bad thing. And usually the techs are the last ones to get laid off, while the engineers and managers are the first ones to get laid off. So food for thought. You know, there's always that career pathway you can do, especially if you do a lot of hands-on stuff. If you take our fabrication classes later on, where you can work in the clean room with myself or Dr. Jackson, combined we have 3 classes you can take in your junior, senior years. You know, that's direct hands-on skills and learning the vocabulary and the technologies in an applied sense. Then you can go out and ask for a job at an Intel or a Mesa facility, or an HT Micro or someplace like that. And if you already know something about photolithography and etch and deposition and metrology and characterization and all that, you'll do really well at your interview, and you'll probably get hired over someone who hasn't done any of that, that may even have a higher GPA than you. Okay, so, you know, keep an open mind in terms of applying for jobs. It's not always about, you know, sitting at a desk in front of a computer designing CAD things. Okay, we got plenty of people who are good at that. You know, that sort of thing is taught fairly well in undergraduate, but the hands-on aspect of manufacturing and fabrication isn't taught as much. All right, so of course, if you have any questions, always feel free to email me. Or send a message through Learn, and I will try to attend to your questions and your homework concerns. So take care, and that's all I have.